All right. So today we're going to have a final lecture in the course, and it's going to be about motor types. So you remember last lecture was about actuator types, and we mostly discussed how we could build a new type of actuator. Let me just remind you a few ideas from the last lecture so you can see the obvious difference between actuator and a motor in this context. The first actuator type that we proposed was a variable stiffness actuator, which contained two different motors. Normally, somehow the word actuator and the word motor seems to be interchangeable, right? Normally you think, okay, motor is just a simple word to describe what is inside an actuator. Actuator is a fancy way to talk about a motor plus every dongle it has on. Here, this is not clearly not applicable, right? Because variable stiffness actuator has two motors inside. So the words clearly are not interchangeable. And when we were talking about new actuator types, we were talking about advanced, maybe experimental ways to work with motors, right? Now, with motor types, what I'm going to discuss now is kind of the opposite end of this spectrum. We're going to discuss the very traditional, the widespread, and well-recognized motor designs, right? We'll go through three types. So in particular, we're going to go through AC motor, stepper, and the brushless motor, and just to understand what is going on. And what I want to convey is partly that all three are quite similar. There is a distinction, of course, but they're quite similar. And with the motor types, I think one of the important messages is to understand how they work, understand where which one is being used. Yeah, as opposed to, and it is, how should I put it? Here we, if last lecture we looked for possible future innovations, here we just get a look for, basic background knowledge. We want to understand which motor does what, right? In modern robotics, at least right now, maybe it will change in the future, but at least right now, we don't see innovations in motor types being used. Instead, we see clever use of existing motor types, such as brushless motor is a good example, have been spreading to new applications again and again and again, with different types of brushless motors being spreading to new applications. So it appears to be important to understand those existing motor types as opposed to maybe innovative designs. Not saying that the innovative designs are not important. They are, first. Okay, let's move into the content. So first, AC motor. The reason I even want to include it here is twofold. One is when you hear DC motor for your entire course, and possibly for half of your education in university, just the logic of the name suggests that the opposite of a DC motor is an AC motor. Okay, that is something that you would think. Okay, so DC, AC, right? Same as with the current, and it is in some sense correct. In some sense, correct. Also, often enough, people would refer to something like, for example, brushless motor as an AC motor. And this can become confusing. So we need to understand how AC motor works, right? But before we do, let's just kind of like make clear that typical AC motor, when we understand it as a traditional AC motor design, is not so much a robotics component as a component of industrial automation. AC motors tend to be large. They tend to be used for applications which require a lot of power, a lot of torque. I don't mean here a lot of torque density, like in quadrotors. I mean just physically large applications, large scale applications. They are oldest type of motor out of what I present here in this lecture. So those motors are quite old, have been used since earliest days of electrified industry. So they are extremely old. They're quite simple to use. I apologize. I think I was kicked out for some reason. Can you hear me now?
Yes.
Okay. Sorry about that. Oh, I don't know what happened. One moment. Okay, hopefully it doesn't happen again. I see. So as I was saying, they are the oldest type of motor used in the industry. And they are widely known partially for that, because they are used in heavy industry. They have been used for a very long time, so people know them, right? Even people in the robotics community would know those motors because they're just like same as DC motor. They are archetypal design. Okay, so that is sort of, you can think of it as a part of a reason why they're important. You can think of back to DC motor, and that we studied in the lecture on motors, right? And you can remember maybe that I said that DC motor by itself is almost never used. We don't use a brush, DC motor as a brush in robotics applications. But the model of DC motor is being used extensively. We pretty much always use it when we discuss motors in robotics content. This context, this model of a DC motor. So the model is extremely widely used, while the motor itself isn't. In a way, a similar situation is with AC motor. The design of AC motor is well understood, while the motor itself is rather in a different area of application. Okay, now let's understand what it is. So the big difference between a DC motor and AC motor on the first glance is the lack of a brush. If you remember, the idea of a DC motor was that we would change direction of the magnetic field by using the brushes that would disconnect one direction of the flowing current through coils and connect another direction. Okay, so the brushes would be acting like a switchboard, you can say, which is automated based on the orientation of the shaft. Different parts of the circuits will be connected, and the direction of the current will be changed. And this is how you achieve continuous rotation. In the simplest example of a DC motor, the polarity in the same coil would be changed, and we would achieve motion. Actual DC motors a little bit more complicated than that, but the idea is still you use brushes to automatically recommute. Okay, for AC motor, the way we do this is slightly different. First of all, it doesn't have a brush in the first place. There is no brush, right? Instead, what we do is we use a few different coils, a few different circuits, and we power them up individually. Right? We power them up individually. So let me illustrate this on this picture here. All right. So in this picture, this part here, like this tooth is drawn, that is, you can think of it as a coil. Like additionally, it has those I would like not to make it too complicated for no good reason, but okay, those two, it has those two wires. Okay, so this wire has current, you can say, coming at us. This wire has a current coming away from us, but in actual reality, it is like a coil through which the current flows, right? And so is, other pairs of coils. Okay. Or if you want, like this picture works also on a different level. You could, if you prefer, you can just think of this as a source of magnetic field, because ultimately, what a coil wrapped around the tooth is, let's say this is the tooth, and we wrap a coil around it like this. Ultimately, what it is a source of magnetic field. So you can imagine this produce magnetic field that flows out, and there would be, let's say, a south pole exiting the end of this tooth. Let's say here at the B, this is the south pole. Let's say, right? That is also how you can try to envision this picture. Ultimately, what happens in a motor is that you have those coils spread around, which produce magnetic field. Either it will be, they will produce a south pole magnetic field or a north pole magnetic field. Now, the rotor, you can visualize it as a magnet. Okay, so on the rotor there will be a magnet, and if you remember how magnets work, if you put a magnet next to another magnet, they'll try to align, right? We can discuss all of this in terms of Lorentz force, as we did with DC motors. But for today, I would just stick to this idea that magnets align, all right? So this direction, north direction of the magnet, right? Let me show. This north direction of magnet would face the south direction of the outflowing magnetic field, right? Now, we could switch on a different pole, right? And then the magnet would try to align with this. Then we could switch on different inductor, and the motor will try to align with this. So it will kind of move around, right? It will sort of rotate towards next pole and next pole and next pole, right? Next coil and next coil and next coil. By changing polarity of those, we could also influence not only attraction but also repulsion. Yeah. Okay. So obviously, the design of the motor will be such that as we switch them on, the magnet would want to move forward by a certain number of degrees. So we constructed carefully in such a way that it would like not repel the magnet, etc. It would exactly go a little bit forward. And in a way, you can think of it like this. We have having three different sources of magnetic field. We can orient the magnet in three different ways, right? At least. And this would correspond to 180-degree rotation. If we allow 360 degrees rotation, it will be 6 different positions that the motor will achieve. One facing one source of magnetic field, then another one, then the same, but it started to change the orientation. So 6 different positions that can achieve. So this somehow implies that there will be a 60-degree gap between those sources of magnetic field, right? Of course, by clever design, we can do much more than that. We don't have to stick to this idea with three sources of magnetic field with this 60-degree kind of step. And the idea of this step will come up later when we discuss the stepper motor. All right. Now, all of this is fine, and this works. But what it means is we have to somehow power those coils on and off ourselves. With DC motor, we just had to provide power to the coil, to the motor windings, and the brush will do all the work. It will commutate it correctly, allow the electrical power to do its work, right? Produce Lorentz force, to rotate our wire, etc. Here, we don't have such a magical device. And this means we have to ourselves provide different levels of voltages to different coils. In a typical AC motor, we would have 3 output wires, all right, corresponding to 3 phases, right? Corresponding to 3 phases. And each of those wires, each of those, you can say, circuits, has to be powered independently, right? So the idea is that you could, now let me see if I have illustration. Right, we'll go there in a second. So the idea is that you could use something like a AC current that is often present, as we say, coming out of the wall. So AC current is AC current is what you have in your house, right? It's 220 volts, 60 hertz, right? Unlike DC current, which is you have in your lab equipment, which is like 5 volts, for example, 12 volts, right? Constant. AC current, it oscillates. It is like a sine wave. It oscillates. It goes from a certain voltage in negative direction, then to 0, then to certain voltage in a positive direction. Okay. In industry, what we often have is what we call 3-phase current. Okay, 3-phase AC current. This means that, and those phases are separated by 120 degrees. So that means that we could use this current directly to power the motor. We could connect those 3 phases to the 3 circuits, like 3 inductor circuits of the motor. And they would provide changing magnetic field, which would do exactly what we described. So it would power, let me try to illustrate. So the power one source of magnetic field, leave another one. Here, I think it might be better if I use this as notation. So to power one source of magnetic field, right? Leave another one, let's say, sort of at zero, and power another source of magnetic field, but in the opposite direction. So what we can expect is somehow the phases to produce magnetic field, which would exactly move the motor a little bit forward, right? And as time goes on, the sine waves coming out of your wall, like three-phase electricity, would shift. Like, so this, what used to be strong magnetic field here would then become a weaker magnetic field. The magnetic field here would gain the opposite direction. Magnetic field here become weaker, and over time, all this will change into, this having no magnetic field, this having magnetic field that faces this direction, this having magnetic field looking like this, and so on. The idea is that as your motor moves along, your three-phase electricity will also move along, rotating the overall magnetic field. And that is a common idea in describing these types of motors. So what we say is something like this. The cumulative magnetic field, if you sum all the magnetic fields produced by individual motors, rotates. So let's say your magnetic field currently is facing this way. So I sum all three magnetic fields and I say, okay, it faces this way. This means that our North Pole, and here I'm sort of simplifying again, I'm using this idea that your magnet will orient itself along the magnetic field. So your North Pole would want to rotate this way, right? Let's say we rotate it, and our motor now faces something like this, right? It rotated a little bit. By the time it rotated a little bit, your total magnetic field will be facing this direction, because your wall electricity has 60 hertz. So it means 60 times a second it completes this full period of a sine wave. So in 60 times a second, it would go all around your motor, this magnetic field. Again, this depends on how you wire your motor. You can do it differently, but it's a rough idea. It's a rough idea. So you rotate your magnetic field simply by using wall electricity. And your motor will again attempt to rotate to align itself with your magnetic field. So it will go like this. By the time it gets there, magnetic field is again a little bit away. This is what we call rotating magnetic field. Now, this would allow us constant velocity motor, right? So your motor would operate at a constant velocity, which is perfectly fine for industrial applications often. Often what you want is just a source of rotation, which you can then control with your gearbox. You don't often need to change your speed of rotation, okay? And this is fine for a lot of tasks. And this is what people do. They want simple design, and this is a simple design. Now, a few words about actual engineering situation of this thing. First, you have to have a magnet here of some kind. Like this has to be a magnet. Now, there are three options. One option, use permanent magnet, the way we draw here. This is a possibility. But with permanent magnets, one slight problem is that often enough, what you want is a series of magnets, not just one magnet, because you want to orient each. How should I put it? You want to have multiple magnets which would react to different parts of the magnetic field and so on. Becomes complicated. Second option is instead of permanent magnet, you can use induce in electric magnet. Okay, so inductor. This is again possible, but then you would have a separate wire running DC current through your through your electric magnet that changes its orientation. That is just a little bit difficult. Yeah. As in, it is additional wire, more work, but people do this too. And lastly, and that is the most popular type that you would find everywhere where you look at the AC motors, is a motor of asynchronous type with a squirrel cage. So what we mean by that is the motor would have a number of, you could say, I would want to describe them as magnetic conductors, basically metal frames, which would have electricity flow through them, induced by the magnetic flux, like the magnetic field, existing inside your motor. So this magnetic field that we are using to provide motion would induce a current to flow through this metal frame. So the metal frame, you can envision it kind of like this. In 3D, it would be something like this. Okay. In 3D, this is something like this. So there will be a current flowing through this metal frame. Now, this current flowing through metal frame means that it produces magnetic field of its own. This is the same principle as with the inductor. Inductor produces magnetic field because there is a magnetic field going through a closed loop circuit, and it just depends on that basically. And if you have more of them, more of the circuits, you have a stronger magnetic field, which is why people use what they call a squirrel cage. So they put not only one frame, but many frames. Like this is a separate frame going like this. Let me illustrate like how should I put it? You can imagine this is one squirrel cage. Sorry, one metal frame. There's another metal frame going like this. There's another metal frame going like this. I'm doing a cross section, so all of them look rectangular. They connect. There's another metal frame, right? What they call here conductive bars. Okay, another one, and so on. What happens when you put it all together is a structure that looks roughly speaking like this. Looks like a cage, you can see. And it reminded people of I guess, a toy. I don't know, some kind of a device to put a squirrel in. I'm not sure, if is very kind to the squirrel. I don't know. But it roughly speaking, something like this. So this is how it looks. Those circles at the at the back, it's just so you can kind of see the connection in the squirrel cage in this. It will in practice be not like a circle, of course, but all those bars that kind of goes like this. Okay, but you can make it clever somehow, because you don't want stuff to be intersecting here. So this reminded people of a squirrel cage, and this is exactly how it's called. So it's a motor with a squirrel cage. So the reason we call it inductor motor is because it uses induced electricity to create magnetic field. So no need for permanent magnet, no need for the electromagnet. And the reason we call it squirrel cage is because it looks like one. Now, the reason we call it asynchronous is because this motor would always lag behind the phase. So it would there was always be a little bit of a lag. Why is there a little bit of lag? Because for the current to be induced, you have to have a like certain phase difference and so on and so forth. So we call it asynchronous motor. Yeah. Whereas synchronous, you can imagine it being kind of like locked in with your moving magnetic field. Okay. As I said, all of this is not robotic stuff, but it is a basic building block for industry. Now, it's not a wasted knowledge what we just found, because we will see more or less exactly the same design for the other two motors. So let's, without losing time, go towards the stepping motor, which we would find already familiar. Now, before I go, let me tell you what stepper motors are used for. So AC motor is a good source of constant rotation. But you could imagine applications where instead of constant rotation, you want constant orientation. So your orientation would have to be something and should remain this exact thing. DC motor cannot provide this. DC motor is a source of rotation, not a constant source of rotation. It can provide you fast rotation, slower rotation, depending on the current, ultimately on the voltage of the input voltage. AC motor that we discussed is a source of constant rotation. It depends entirely on the speed on the frequency of change of magnetic field. Yeah. 1 second. Let me double check that everything is fine. Yeah, I think everything is fine. So you could control the velocity of AC motor by using a special type of machine, which would change your basically three-phase electricity into three-phase electricity with different frequency. You could do that. It's quite complicated, and yeah, we will come back to this when we discuss brushless motor. But yeah, the AC motor is a source of rotation. Now, stepper motor is the idea is to produce a source of orientation. Make sure that we have a motor that can orient itself very precisely. Okay. Now let's look at what it is in terms of diagram. And this is a diagram. Let me just explain to you what is shown here. So these guys are sources of magnetic field, just like before. So here, for example, you can imagine this is the North Pole, this is the South Pole. Okay. All right. Here, for simplicity, if you want, you can think of this as a permanent magnet that wants to orient itself like this, facing north and south. Here, though, this particular one that we see here is not actually like this central thing is not a magnet. Rather, it is closer to being a magnetic conductor. But for our purposes, we don't need to go into this level of detail. Let's just think of it as a magnet, because it will just simplify for us the way we think about it. So you can imagine the magnet, or this central, I'll call it a magnet just to make it simpler for us, was oriented like this, right? Now what it wants, that this motor is being switched on, is to orient like this. And the simple way to do it would be to rotate in this direction, because there's like, there is this slight asymmetry, like in this direction. So that's what it does, and this produces a rotation. Now, next step, it is already oriented like this, and everything is fine. But then we can switch on a different pair. Let's say we can switch on this pair, okay? And it will try to continue rotation. So this time, what will happen is to orient again along this axis, it will rotate a little bit here. You can see that this part wants to align with this pair if we switch it on. So that's exactly what we will find here. Basically, you can think of steppy motor design as exactly the same as AC motor design, where we switch on switch on the sources of magnetic field and our magnet. In this case, it is slightly different, but yeah, let's say our magnet orients itself along the magnetic field. So this is, if this was a magnet, it would be called a permanent magnet type motor. Okay. All right. All right. So far, finding a difference between this and the AC motor will be an exercise in philosophy. Okay. The design looks almost exactly the same. Okay. Now, the actual DC motors that you use in your lab, those look nothing alike the AC motor that people find in the industry. And the reason is people want to the steps not to be 60 degrees. They want the steps to be 1.28 degrees. So the typical number is 1.8 1.8 degrees. Okay, that's a typical number. And that is done by changing the design a little bit. So the design would include indeed south and north pole. So permanent magnet, south north pole, but is a little bit complicated to say the least. So north pole will be this gear, you could say. South pole will be this gear, and they would be misaligned. So the teeth of one gear would correspond to the gaps of another gear. Right? That's not very important for what I'm going to say. I'm just sort of indicating how it is built. Now, what is important is, let me go next slide, if I can. Okay. What is important is how those teeth help us move forward. And the way they do is something like this. We have outer teeth here, and we have inner teeth here. Those inner teeth are the teeth of your rotor. Outer teeth are the teeth of your stator. Now, they are slightly misaligned. As you can see, these teeth here align perfectly with the teeth here, right? There's a perfect alignment. While here, there's clearly a misalignment. And here the teeth manage to misalign so much that they look at the gaps instead of the teeth. Okay. So if we had a continuous ring of teeth on the stator, what we would see is that there are fewer teeth on the stator than there are on the rotor. So this on purpose made unsymmetrical in the number of teeth. Okay, how is it useful? Well, let's say that this pole is switched on. So the magnetic field flows like this. This is only one that is switched on, this source of magnetic field, okay, electric inductor. Now, the teeth are perfectly aligned. Everything is great. So the motor would stay in this position. Right? This, if you think of this as the permanent magnet, it will stay in this position. Okay. Here, this picture is 2D, but you remember that the north pole is a little bit at the back of the motor. So if to make it less confusing, imagine that we are only speaking about the upper part of the picture, just to be kind of like a little bit less in danger. So let's say that we are speaking about this. And the low part, if you want, you can imagine it being at the back a little bit. So when I say that magnetic field flows like this, what I mean is here the north teeth are aligned, like the other pole is aligned correctly. The teeth from the other pole is aligned correctly. And here is the, like, this is can be, if you want, the south pole teeth. This is north pole teeth, if you want. Okay, those details are not very important. We're not building a motor. But if you abstract from like how it's done mechanically, as in where the teeth are physically inside this motor, so far it's exactly the same picture as what we saw previously with AC motor. We simply align our magnet, like in this case, those teeth, with the source of magnetic field. Okay, all right. Now, let's say we switch on, and by the way, what happens here is irrelevant because those are not switched on, like those source of magnetic field are not switched on. So it doesn't actually matter what happens in there. What matters is what happens here. Now, let me imagine that we change our direction of the magnetic field. Now we switch on the D circuit. We switch on the D circuit. Now what happens is the teeth here are slightly misaligned. So they would want to come into alignment by rotating the rotor a little bit. So they will come into alignment. And now the situation would be exactly the same as in the beginning, but the rotor would have had rotated. But the gap between the teeth here would become exactly the same as it was for the teeth here early. So next time we can switch on the D circuit, we will achieve the same stuff. So what we could do is we could switch circuits like A, B, C, D, or in this case, the way I decided to do it for some reason, D bar, C bar, B bar, A bar. And it would rotate, little by little to rotate. And depending on in which direction I will switch them, they would rotate clockwise or counterclockwise. Okay. And we can align the motor with the precision of the alignment of those teeth. Now, there is another way to increase further the accuracy of the motor. And that is to switch two poles, like two sources at the same time. Let's say this one and this one. What would happen then is both teeth will try to align. Let me clear this. We switch on this and this is the same thing.
Yes.
Yes. Was the question also?
I said it's clear.
Okay. Yeah. Thank you. Thank you. So let's say we switch them both at the same time. And what will happen is this one is slightly misaligned. So it would want to align. This one is perfectly aligned. So it would kind of resist the change. But it would have to shift a little bit because of this one trying to misalign. So at the end, they would kind of align as if the magnetic field works in this direction. This is called half stepping. So this would allow us to shift not between the poles like this, but in between them as well. So it's like half step. You can do something that I believe people call microstepping when you change the relative power of magnetic fields. But half stepping is a popular method that is like widely, I think, almost universally used. Now, this, as you can see, is still exactly the same as AC motor. The only difference is we have those fine, small teeth, right? Fine, small teeth. Those teeth are exactly what makes the difference. AC motor doesn't have this kind of stuff. AC motor, if you remember the design, you have the squirrel cage inside. What we care about is just constant rotation. There's no question of anything finely oriented there. Like any of those teeth would be kind of pointless. Here we have the teeth that look again like this, something like this. And they are meant for us to be able to stop at a certain position. So if you want to think about it this way, you can say that the two motors are the same type of motor, but one is being built for constant rotation at a constant speed, while the other is being built for being still in a certain position. So one is the source of constant rotation. This is the source of variable position. Okay, all right. Before I move to the next one, let me say a few words about brush stepper motor. So they have some characteristics. One characteristic is they are heavy. As you can imagine, like look at this design. So much metal. They're heavy. Torque density is less than for other types of motors. And in general, they are not good source of constant rotation. So if you're going to rotate something, use a different type of motor. If you're going to position something, then it is fine. That is why these motors are usually used in stationary stuff. For example, 3D printers, obvious application for placing something in the correct position. That is where stepper motors are used. They're used in various other stationary robots, but not where you need a lot of torque. So KUKA robot will not use a stepper motor because the weight will be high, while the torque would not be as high as what you would wish. So stepper motors are not something that lifts loads, not something that produces constant motion. Like you don't run a fan using stepper motor. But for precise orientation, for example, if you have an optical drive, like you know how back in the day we used to have something that rotates your CD in your CD-ROM, or whatever it was called, you could use a stepper motor there if you want to. Even in your hard drive, I'm not entirely sure. if the modern ones use stepper motor, but something of the kind. And the line again is blurry between stepper motor and other types of motors. To me, when I rotate a motor and I can feel the inertia going up and down as I rotate, because it kind of passes through different those different you can say orientation of the magnet. That is when I can tell it is a stepper motor, like kind of like on a visceral level, like holding it in your hands. Whereas, for example, brushless motor or AC motor will not feel, like you can rotate the shaft, you will not feel anything. But stepper motor, you always feel this kind of clicks, like soft, but noticeable clicks. Yeah, so they are nice motors to use, but for their specific area of application, you cannot use them for instead of AC motors, for example. Specifically, you cannot use them instead of brushless motors, which is the next topic. So brushless motor is a source of torque. Brushless motors are built to provide high velocity motion, which would generate large torque. The most famous application for brushless motors in robotics had been quadrotors, so drones with propellers. It was when brushless motors were available on the market that the drones started to fly. Right now, walking robots start to walk cheaply and reliably because a different type of brushless motor became available on the market. This time, much bigger one. So for robotics, brushless motors appear to be one of the quintessential components if we are talking about mobile robotics. They are a source of torque. Now, let's try to understand how they work. By now, familiar picture. The reason I even put it separately is just to make sure I don't use the diagram for AC motor to explain a BLDC motor, a brushless motor. Yeah. Is the exact same thing. You have sources of magnetic field. They sum to a magnetic field that goes into a certain direction. And your permanent magnet, and for brushless motors, it is a permanent magnet in the center, would try to orient itself according to magnetic field. So it would try to change orientation, and this produces rotation. Now, what is different between brushless motor and a AC motor is the fact that brushless motor is not built to be run by the wall current. So you don't put three-phase electricity through brushless motor. In the first place, they're quite small compared to industrial motors. And the way we control them is by generating the different levels of voltage on different coils by using a switchboard, so what we call a controller for the motor. We call it a driver, the thing that switches electricity, and there will be a controller that decides how to switch electricity. If you ever saw how drones are built, you always notice that the motor comes with 3 wires, and then there will be a small board which you put the wires into, right? You don't put anything else. Like the wires don't go somewhere. They always go to this special board, which comes with the motor. You buy them together, you can see. This is what is going to connect those wires correctly, so you can generate your magnetic field. Now, in which direction you generate magnetic field, you have to decide. And here comes the interesting part of it. You cannot, one second, sorry. You cannot do it at random. Like what you have to do if you want to rotate it is to go from, let's say, this orientation, which is like here right now, to magnetic field, to new orientation, which would be slightly offset. Like your magnetic field should be slightly offset, but you cannot do it, for example, by just giving it a random direction. For example, let me say, let's say I'm creating this magnetic field. Okay, this will not work because it is orthogonal to the direction of the magnet. Is just not going to be efficient. And if I put my magnetic field like this, is also is not productive. Right? So you want to magnetic field to be slightly ahead of your rotor, basically. This implies you have to know where your rotor is. That is not what we had to do with the DC motor. And by clever design, we could avoid it with other motors. Stepping motors, they generate orientation. So almost by definition, you more or less know where you are. And if you don't know, you just go once, like one full, what do you call it? One full cycle, and you'll be fine. So it's easy enough. In the stepper motor, you don't run in a situation where your during operation, you don't run in a situation where your orientation matters and you don't know what it is. Here, the situation will be constant because if you don't know where you are, and how would you know where you are? You don't know how to put your magnetic field. Okay. For AC motor, we could just hope that the position will be locked in if it is a synchronous motor. And for asynchronous motor, like this design is a birdcage, and other cleverness will save us. I'm not going into details there. Here, we have this problem, we have to solve it. There are two ways people solve it. One way, install a sensor. We use the Hall effect sensor to measure orientation. This allows us to directly measure orientation of the rotor, and we use it directly. This is expensive, but precise. Another option is to analyze back EMF. You remember from our model of DC motor, the back EMF term was present in the Kirchhoff equation. It's basically actual voltage that you can try to measure. They sometimes measure it, and based on back EMF of 3 coils, they'll be able to tell orientation of your permanent magnet inside your motor. Of course, like all of this is nice, but also a whole big part of why brushless motors are so widely used is because the design is very specific. They are very lightweight. They're built to dissipate heat fast. For drone design motors, and even for modern motors that are used in walking robots, often the entire upper half of the motor is rotating because the rotor is not a cylinder inside the motor. Sometimes it's like half of the motor is the rotor. So the magnets sometimes are placed on the inner surface of the motor. The coil would be at the center. So it's cleverness abounds. I'm not going to go into details of all of this, but you can find perfectly good illustrations on YouTube, so you can just look how those motors work, how they look like, etc. What is important for us is this motor appears to be, again, copy of AC motor. Okay, but the difference is we don't plug it into a wall. Instead, we plug it into a controller. which generates for us various voltages with various coils. Okay, that is the first difference. Second difference, we need to know orientation, which we somehow were able to get away with previously. We didn't have to do it previously. Now we have to. Okay. And this basically for us is a extent of the difference. And for us, this operates as a source of a large torque. Now, for walking robots, this is used without thinking about three phases. So I've seen people using those motors. They don't think about three phases. In a way, all of this can be abstracted away if you do it as a servo motor. So if you create a control loop, which will generate your desired torque, while everything else is handled inside the loop. That is a very typical approach. Pretty much always in robotics, we use some kind of servo design where you would have either output position, like if you remember those toys from the 2000s, where you have walking robots on servo motors, they would kind of like vibrate and everything. That will be position control servo motors with DC motors inside. Those work. They were cheap. That was the reason why they used DC motors there. With drones, for example, you want constant angular velocity as output of your drone. And with, let's say, walking robot, you would want a constant source of torque as output of your motor, right? All this can be achieved with a control loop, which would just do that. All right. So this was a short introduction. I hope it illustrated some stuff for you. In a way, maybe if at least you saw that all three of those motors are quite simple and very similar to each other, that maybe would be enough for me. I would be happy if at least this message you got. Now, we will stop the recording and then we can have a Q&A after 5-minute break, I guess.